Hi everyone, welcome back to the channel Quantum. Today we're diving into some of the most foundational aspects of quantum mechanics, its postulates, the von Neumann processes, and the Heisenberg picture. Quantum mechanics is built on a set of core postulates that describe everything from the nature of quantum states to how they evolve and interact with measurements. These postulates are brought to life through von Neumann's two processes. Process 2, which describes the smooth, deterministic evolution of quantum systems, and Process 1, which handles the collapse of quantum states during measurement. But we won't stop there. We'll also explore the Heisenberg picture, an alternative framework to the Schrödinger picture, which focuses on the evolution of operators rather than states. This will lead us to the profound connection between quantum mechanics and classical mechanics, through the process of canonical quantization and its inverse process, the semi-classical limit. If you love exploring the deep ideas, insights, and perspectives of theoretical physics about the world, please make sure to hit the like and subscribe buttons and feel free to leave a comment. I'd love to hear your thoughts and suggestions for future topics. Let's get started. First, let's summarize the 5 postulates that form the framework of quantum mechanics. State vectors. The state of a quantum system is described by a vector, or ket, that resides in a mathematical structure called a Hilbert space. Observables. Any measurable quantity, such as position or energy, is represented by a Hermitian operator that acts on the state vectors within this space. Dynamics. The evolution of a quantum state is deterministic, unitary, and reversible. This evolution is described by equations like the Schrödinger and Heisenberg equations. Measurement. Quantum measurement, however, is non-deterministic, irreversible, and non-unitary. Measurement collapses the quantum state to a specific outcome. Composite systems. When two systems are combined, their joint state is represented by the tensor product of their individual Hilbert spaces. This is critical for understanding phenomena like entanglement. With these postulates in place, we can now explore the von Neumann processes. Von Neumann, a key figure in quantum mechanics, described the behavior of quantum systems using 2 distinct processes, Process 2 and Process 1. Let's take a closer look. Process 2, unitary evolution. This process describes how a quantum system evolves over time in a smooth and deterministic manner. It's governed by the Schrödinger equation, given in equation 2.1. This equation allows us to determine the state of a system at any point in time, provided we know its initial state. One key feature of Process 2 is the principle of quantum superposition. If two states, let's call them psi1 and psi2, are solutions to the Schrödinger equation, then any linear combination of these states is also a valid solution. This principle underpins much of the strangeness of quantum mechanics, where particles can exist in a combination of multiple states simultaneously. Process 1, collapse or reduction. Now, let's move on to Process 1, the collapse or reduction postulate. This is where quantum mechanics diverges from classical determinism. When we measure an observable in a quantum system, the state of that system collapses to one of the eigenstates of the operator associated with that observable. The result of this measurement is one of the eigenvalues tied to those eigenstates. Let us assume that the state of the system is given by the Dirac ket psi of t. We are interested in the measurement of the observable O, which is a Hermitian operator characterized by eigenvalues lambda I and their corresponding eigenvectors ket vi. We further assume that these eigenvectors form an orthonormal basis. We expand then the state psi of t in this basis, as shown in equation 2.2. The coefficient Ci of t gives the probability amplitude of obtaining the eigenvalue lambda I when we measure O in the state psi of t. The probability of observing a specific outcome and the post-measurement state are given respectively by Born's rule and the collapse postulate, given in equation 2.3. Born's rule, in the first line of equation 2.3, states that the square of the amplitude of the state vector gives the likelihood of obtaining a particular eigenvalue. After the measurement, the state of the system collapses to the eigenstate corresponding to the observed outcome, as shown in the second line of equation 2.3. A fascinating aspect of quantum mechanics, projective measurement, also known as Process 1 in von Neumann's framework. This concept is essential for understanding how quantum systems interact with measurement. Let's break it down step by step. Let's start with a physical system, which we'll call S. In quantum mechanics, the states of this system are represented as vectors in a Hilbert space, denoted as H. Now, within this system, we may want to measure physical observables, such as position or momentum. These observables are represented by Hermitian operators acting in the Hilbert space. A key property of Hermitian operators is that their eigenvalues, the possible outcomes of a measurement, are real numbers, which makes them suitable for representing measurable quantities. Here's where it gets interesting. Not all observables can be measured simultaneously. For example, position and momentum are incompatible observables. This incompatibility arises because their corresponding operators don't commute. That is, the order in which you apply these operators matters. Mathematically, O1 times O2 is not equal to O2 times O1. The first measurement. Suppose we measure the observable O1 at a specific time, T1. The result of this measurement will be one of the eigenvalues, say P1. This measurement is represented in the Hilbert space by a projection operator, P1. Projection operators are special because they are idempotent, meaning P1 squared equals P1. They act to project the state of the system into a subspace corresponding to the measured eigenvalue P1. Now, what's the probability of obtaining P1? According to Born's rule, this probability is calculated as the trace of the product of P1 and the initial state's density matrix, rho 0, as shown in equation 2.4. The proof for this assertion is shown in equation 2.5. This gives us a concrete way to predict measurement outcomes. Once we've measured O1 and obtained P1, the system's state collapses. The new state is described by a density matrix, rho 1, which is updated using von Neumann's rule, given in equation 2.6, and written explicitly in equation 2.7. This formula essentially renormalizes the state based on the outcome of the measurement, the second measurement. Now let's add a second measurement into the mix. Suppose we measure another observable, O2, at a later time, T2, and find the eigenvalue P2. This measurement is represented by another projection operator, P2. The probability of obtaining P2, given that we already measured P1, is calculated using the updated state rho 1. This is another application of Born's rule, as shown in equation 2.8. But what if we want to know the probability of both measurements happening sequentially? This joint probability is simply the product of the two individual probabilities, as expressed in equation 2.9. Furthermore, and as before, the post-measurement state is a collapsed state, given in this case by equation 2.10. Generalizing to multiple measurements, we can extend this idea to a sequence of measurements over time. For example, if we have n measurements, each represented by a projection operator P1, P2 until Pn, we can calculate the probability of this quantum history using a generalization of Born's rule. The formula is outlined in equation 2.11. Similarly, the state of the system, after all n measurements, is described by a generalized collapse postulate, which state that collapsed state after these n measurements is the state associated with the reduced density matrix shown in equation 2.12. This approach provides a consistent framework for understanding how quantum states evolve under successive measurements. Next, we're tackling a cornerstone of quantum mechanics, the Heisenberg picture and Heisenberg algebra. We'll thus explore how quantum systems evolve in this picture and how this perspective compares to the Schrödinger picture. More importantly, this will allow us to describe the process of canonical quantization, how we go from classical mechanics to quantum mechanics, and the reverse process of the semi-classical limit, how we go from quantum mechanics to classical mechanics. Let's dive in. To understand the Heisenberg picture, we first need to revisit the Schrödinger picture. In this framework, the time evolution of a quantum state is governed by the famous Schrödinger equation. This equation emerges from the correspondence principle, shown in equations 2.13 and 2.14, where classical variables like position and momentum are replaced by quantum operators on the Hilbert space. The Hamiltonian operator in this case, as referenced in equation 2.15, is built from these quantum operators and acts on state vectors in a Hilbert space. The Schrödinger equation then tells us how a quantum state, represented as a Dirac ket, evolves over time, as shown in equation 2.16. The solution to the Schrödinger equation can be expressed using a unitary operator, as given in equation 2.17. This operator evolves the quantum state from an initial time t0 to a later time t. As before, given the spectral decomposition of Hermitian operator hat O, which is shown in equation 2.18, we expand the state vector psi of t in the eigenbasis of the operator hat O, as shown in equation 2.19. The expectation value of the observable hat O, calculated in the state psi of t, is then given by equation 2.20. In other words, we take the inner product of the state psi of t with the state obtained by acting with the operator hat O on psi of t. Importantly, the operators representing observables, like position or momentum, are fixed and do not change with time in this framework. The time-dependent state vectors psi of t, denoted now by psi subscript s, and the fixed operator hat O, denoted now by hat O subscript s, define the so-called Schrödinger's picture, which is summarized in equation 2.21. Now let's transition to the Heisenberg picture. Here, the roles of states and operators are reversed compared to the Schrödinger picture. In the Heisenberg picture, the quantum state is fixed, while the observables, represented by operators, become time-dependent. This is achieved using the unitary operator mentioned earlier. More precisely, this is achieved by requiring that the expectation value of any observable to be the same in both the Schrödinger and Heisenberg pictures. Indeed, the above expectation value can be rewritten in terms of the time-dependent Heisenberg operators, denoted by hat O subscript h, and the fixed Heisenberg states, denoted by psi subscript h, as given in the first line of equation 2.22. The time-dependent operators and fixed states of the Heisenberg picture are shown explicitly in the second line of equation 2.22. In particular, the Heisenberg operators are given by a similarity transformation of the Schrödinger operators, which is defined by the unitary evolution operator. Although the Schrödinger and Heisenberg pictures, called also wave mechanics and matrix mechanics respectively, might seem different, they are mathematically equivalent. The expectation value of an observable is the same in both pictures, as shown in the first line of equation 2.22. This equivalence ensures that either picture can be used to describe a quantum system, depending on the context or convenience. The Heisenberg picture is defined in terms of the Heisenberg equation in the same way that the equivalent Schrödinger picture is defined in terms of the Schrödinger equation. The time evolution of an operator in the Heisenberg picture is derived in equation 2.23 from the requirement that the expectation value is the same in both the Schrödinger and Heisenberg pictures, together with the Schrödinger equation. This equation describes how an operator evolves over time due to its commutator with the Hamiltonian. Thus, in the Heisenberg picture, the time dependence of an operator is described by the Heisenberg equation. For operators that explicitly depend on time, an additional term is added to account for this dependence. The full form of the Heisenberg equation is then given in equation 2.24. Interestingly, the Heisenberg equation closely resembles Hamilton's equations from classical mechanics given in equation 2.25, which are written in terms of the Poisson brackets. Indeed, in the classical limit, when h bar goes to 0, the quantum commutator reduces to the classical Poisson bracket as described in equation 2.34. This connection between classical and quantum mechanics highlights the foundational role of the Heisenberg picture in bridging the two frameworks. Let us discuss this central point a little further. Let's consider two key examples in the Heisenberg picture, the position operator q hat subscript h and the momentum operator p hat subscript h. The Hamiltonian, when expressed in the Heisenberg picture, retains the familiar form, representing the total energy of the system as the sum of kinetic and potential energy. This serves as the starting point for deriving the time evolution of operators in the Heisenberg picture. First, we compute the time evolution of the position and momentum operators. Using the Heisenberg equation of motion, we find that the rate of change of the position operator q hat subscript h depends on the commutator between the position q hat subscript h and the momentum p hat subscript h. Similarly, the rate of change of the momentum operator p hat subscript h is linked to the commutator between the momentum p hat subscript h and the potential energy term. In summary, we find equations 2.27 and 2.28. Interestingly, the equations of motion derived in the quantum framework mirror the classical Hamiltonian equations of motion. For example, the time evolution of q hat subscript h corresponds to the classical equation stating that the rate of change of position is equal to the momentum divided by the mass. Similarly, the time evolution of p hat subscript h agrees with the classical rule that the rate of change of momentum equals the negative gradient of the potential. These parallels highlight the deep connection between quantum and classical mechanics. We want therefore equations 2.27 and 2.28 to reduce to equations 2.29 and 2.3u, respectively. The solution is given by the celebrated Heisenberg algebra, which is defined by the Dirac fundamental commutation relation shown in equation 2.31. This is also known as canonical quantization. This ansatz is consistent with the correspondence principle 2.113. In fact, equation 2.13 furnishes a differential representation of the Heisenberg algebra 2.31. The Heisenberg algebra, as given by the Dirac fundamental commutation relation 2.31, allows us to bring immediately the quantum equation of motion 2.27 to the canonical form 2.29. In order to bring the quantum equation of motion 2.28 to the canonical form 2.30, we need to consider polynomial potentials as demonstrated in equation 2.32. At the heart of the Heisenberg picture lies the Heisenberg algebra, defined by the fundamental commutation relation between q hat subscript h and p hat subscript h. This relation, known as the canonical quantization condition, encodes the quantum mechanical structure of the system and serves as a cornerstone of the theory. This commutation relation also ensures consistency with the correspondence principle, which bridges quantum mechanics and classical physics. By using this principle, the quantum equations of motion naturally reduce to their classical counterparts in the appropriate limit. Now, let's delve into the semi-classical limit, where quantum mechanics transitions smoothly into classical mechanics as h bar approaches zero. In this limit, quantum effects become negligible, and the commutator between operators reduces to the classical Poisson bracket, as indicated in equation 2.34. This is sufficient for quantum mechanics to reduce correctly to classical mechanics in the semi-classical limit. Indeed, the Heisenberg equation of motion of the observable hat O subscript h, given in equation 2.24, reduces, in this limit, to the classical Hamilton's equation of the corresponding dynamical variable O, given in equation 2.25. For example, it is clear that the quantum equations of motion derived in equations 2.29 and 2.30 reduce to the standard Hamilton's equations given in equation 2.33. Equivalently, in the semi-classical limit, the wave function of a particle becomes sharply peaked around its classical trajectory, and as a consequence, the Schrödinger equation simplifies to the Hamilton-Jacobi equation of classical mechanics. This is shown explicitly in equations 2.36 through 2.40. The transition outlined by the semi-classical limit indicated in equation 2.34 is more than just mathematical. It reveals how the quantum world, with all its probabilistic strangeness, connects to the deterministic laws of classical physics we're familiar with. The equivalence between quantum and classical mechanics in the semi-classical limit when h bar approaches zero is striking. The Heisenberg picture, with its emphasis on operators and their commutation relations, provides a fundamental framework for understanding this transition. The Heisenberg picture provides also the proper framework for the transition from the classical to the quantum descriptions, which is a process known as canonical quantization, in which Poisson brackets are quantized by replacing them appropriately with commutators. In our view, the Heisenberg algebra, defined by the fundamental Dirac commutation relation, is more fundamental than the Heisenberg equation itself, in the sense that the former defines the underlying Hilbert space structure, whereas the latter provides the dynamics. In fact, the Heisenberg picture, with its underlying Heisenberg algebra and Heisenberg equation, is more fundamental than the Schrödinger picture, with its underlying Schrödinger equation, in the same way that in classical mechanics, the Poisson bracket, limit of quantum commutator, is more fundamental than the Hamilton-Jacobi equation, limit of Schrödinger equation. And that wraps up today's exploration of quantum mechanics. We've discussed the fundamental postulates, von Neumann's two processes, and the Heisenberg picture. We've seen how these ideas not only provide a complete description of the quantum world, but also offer insights into how quantum mechanics transitions to classical physics in the semi-classical limit. If you enjoy exploring the mysteries of the quantum world, don't forget to like this video, subscribe to the channel, and leave a comment. Your support helps keep this journey into theoretical physics alive, and I'd love to hear what topics you'd like to see next. Thanks for watching, and I'll see you in the next video.